let's tackle on a definition of thermodynamics. So thermodynamics is a branch of physical sciences that is concerned with the ways of energy is stored within a body and how energy transformations, which involve heat and work, may take place. So basically, the word thermo here means it involves heat. The word thermo means heat. This dynamics involves work. So thermodynamics involve heat and work. So heat is an energy and also work is a form of energy. Okay, so in the latter topics, it's also thermodynamics also is concerned on energy and the entropy. So let's consider now we have two approaches in thermodynamics. One is the macroscopic approach. You have two approaches. Macroscopic approach, and we have the microscopic approach. So the macroscopic approach, this is concerned with the gross or overall behavior of matter based on a large number of molecules, and it is also termed as the classical thermodynamics. Well, the microscopic approach is more concerned directly with the molecular structure of matter, and it is based on the average behavior of groups of individual molecules. This is also termed as statistical thermodynamics. So in the macroscopic approach, we will focus on attention here, because when you're dealing with when you compare the macroscopic and microscopic, if we're going to consider the microscopic approach, so in principle we could solve for the forces acting in every molecule and use Newton's laws to determine the behavioral systems. This is difficult for even modestly sized systems. So if we had, for example, a volume of we have one cubic meter. So you have a volume of 1 cubic meter of gas, assuming this is gas. Here, this is filled with gas. At given atmospheric pressure and temperature, you would find that it was composed of 2.4 times 10 to the 25 number of molecules. So we're dealing with the individual molecule to consider the microscopic approach of thermodynamics. So you know that you need six equations of motions. 6 equations of motion for each molecule. You know that we have, considering we have these 3 dimensions. You have the x and the y and z dimension. Of this x, y and z. So for only 1 cubic meter of gas at given atmospheric pressure and temperature, you have 2.4 times 10 to the 25 number of molecules. So, considering we have a velocity here, we have this Vx, Vy and Vz. So this would require a total of 1.4 times 10 to the 26 differential equations to solve simultaneously. Okay. So even with our largest computers, this is impossible today. Note that most desktop computers can only store roughly 10 to the 9 bytes of data in the random access memory. So we can, however, model the average behavior of the molecules statistically. We can also use simple empirical relations which can be formally proved to capture the statistical nature of the flow. So the classical thermodynamics will treat macroscopic effects only and ignore individual molecular effects. For example, molecules bouncing off a wall exchange momentum with the wall and induce pressure. We could use the Newtonian mechanics for each particle collision to calculate the net force on the wall. Instead, our approach amounts to consider the average over space and time of the net effect of millions of collisions on a wall. So that's why we need to consider the macroscopic approach. This one. We will not consider the or we will neglect the individual molecules, considering a given volume at a given pressure and temperature. So, before we move on, we need to define some terms. So, we have a so-called thermodynamic system. What is this thermodynamic system? Thermodynamic system comprises a device or a combination of devices containing a quantity of matter or a region in space chosen for study. So you have this one. You have our system. This is device or devices that has quantity of matter and will be considered for our study. Okay, device or devices or a combination, like for example pumps, compressors, turbines, and other devices, mechanical devices. Okay, so outside the system we have this surroundings. We have the surroundings, so and here is the system boundary. And the system plus surroundings, this is what? This is called the universe. Okay, remember our Venn diagram in our algebra? We talk all about sets. You have that universe. Okay, let me recall. Here set A, you have this outside the combination of set A plus the surroundings is the universe. Okay. So we have the you have also to consider the kinds of you have the kinds of thermodynamic system. So number one, we have the closed. You have the closed system. Wherein no transfer of mass across its boundary. Energy can flow across the boundary. Second is the open system. So open system, or is called the control volume, wherein mass and energy can flow across the boundary. And we have third is the isolated system, wherein isolated system mass and energy cannot flow across the boundary. So for example, you have this figure, considering you have a system here. So for control volume, this is our system boundary here. This is our system boundary. So for control volume, we have this control volume. It is called an open system, wherein mass and energy can flow across this boundary. Okay, we have mass and we have this energy also, and they're just going to or outside the system. And for the isolated system, the mass and energy cannot cross, or the mass and energy cannot flow across the boundary. So the boundary of the control system is also called our control surface. So for our control volume, in this open system, this boundary here is called the control surface. Okay. So you also define what is thermodynamic property. Thermodynamic property, it is a macroscopic characteristic of a system such as mass, volume, pressure, and temperature, to which a numerical value can be assigned at a given time without knowledge of the previous behavior or history of the system. So again, macroscopic characteristic is considered. Okay, so you have these types of property. We have one is the extensive properties. This refers to the property that dependent on size. Its value for an overall system is the sum of its values for the parts into which the system is divided. So dependent size, like what? Volume. Okay. So that's extensive property. So second, we have this intensive. Have the intensive property or properties. This is independent on size. Its value for the system is not additive. So this is independent on size. So like for example, the temperature, it's an intensive property because given a body, like for example piece of chalk, have a piece of chalk here. If you given this temperature, so cut this one into two, cut this chalk into two pieces, so the value of temperature does not change. So size doesn't matter. And we have also specific properties. in those of a unit mass. So intensive by definition. So again, we have the types of properties or types of the thermodynamic properties. We have this extensive properties, and the intensive properties. Okay. Extensive property example is volume, because it is additive. It is dependent on size. So second is the intensive properties, which is independent on size, like temperature, pressure. Okay. So the mass also is an example of extensive property. Okay. So you have another one. Have this thermodynamic state. Refers to the condition of a system as described by its properties. A system is said to be at steady state if none of its properties changes with time, and it is a point function. That is, it is defined by at least two independent properties. It's defined only when the system is in equilibrium. That is, no change in the value of any property of the system. Okay. So another one you need to define is the what is a process? So a process is a transformation from one state to another. You have a change in state in here. Of course, it occurs when any of the properties of a system change. Defined only when the system is not in equilibrium. So also it is defined by its initial and final state. So for example, we have at point 1, we have at point 2. So a process has an initial state at point 1 and also a final state at point 2. So this is considered to be a process because you have two states wherein you have initial and the final state. Okay. So meaning to say we have the we have a system change. We have properties of point 1 is differs to the properties of point 2. Okay. or the same, or it is constant if we are considering you have a reversible process. So that the reversible process can be tackled in the later topics. The next topics. But here we just define what thermodynamic process is. So process is characterized by a property that remains constant. As I said a while ago, the state 1 to state 2 could be the properties of state 1 is the same or constant at point 2, or the properties at in the initial state is the same with the final state. So are to consider the property that remains constant given the process. Okay. So 1, we have the isobaric. Isobaric process meaning we have constant pressure. Okay, in our PV diagram, we have state 1 and state 2. So we have constant pressure, isobaric. So pressure at point 1 is the same at point 2. Okay. Next we have the isometric. Isometric, or in other books could be termed as isochoric process. So for isochoric process we have constant volume. So in our PV diagram, so we have this constant volume. This is vertical. This is point 1, point 2, or we have a reverse direction. This is our point 1 and this is our point 2. So this is a vertical line, meaning to say in our PV diagram the volume is constant. Okay. Another one, we have isothermal. For isothermal, we have the temperature is constant. So if you have this temperature versus volume, so our process is constant temperature. No, no. We have this horizontal line. Have 1 to 2. This is constant temperature. Okay, and have also this isentropic process. So for isentropic process, this is considered to be that the entropy is constant. So entropy will be discussed in the next topic. So this is just the to show you some processes that has property that is constant. So as a recap, we have isobaric, meaning constant pressure process. The isometric, we have the constant volume, and the isothermal, we have the constant temperature, and the isentropic process, we have the constant entropy. So last, we have a cycle. What is a cycle? Or what is a thermodynamic cycle? Thermodynamic cycle, this is a sequence of processes that begins and ends at the same state. So we have this state 1 here. This is our state 1. In this process. So this is equivalent to our state 2. So we have a process. We have a cycle, thermodynamic cycle. So the initial state and the final state is constant. So meaning to say, the final state of a cycle, all properties have the same values they had at the beginning. So the values at state 1, like for example the pressure, temperature, and other properties, is the same at state 2. Obviously, because the process that begins and ends at the same state.